Thanks for joining us today. My name is Katie Maxfield, and I'm here today with my colleague, Eric Ma. Eric is in our sales and support department, and Eric's going to be giving you a demonstration of SeqMan Ultra. And for those of you who don't know, SeqMan Ultra was released earlier this year, and we've got some new updates coming to the software very soon this summer. So we'll be sharing some of those new updates with you and also introducing you to this new application. Before we get started, just a few housekeeping items. If you have questions, we'd love to be able to address those during today's webinar, so we'll have some time for that at the end. So please send in any questions you have using the question panel. You should see that on the right of your screen in the little go to webinar toolbar, and you may need to expand that using the orange arrow. So send in those questions and we'll address as many as we can during the webinar today. And any that we don't get to, we will follow up with you after the webinar. And yes, the webinar will be recorded. We post all of our webinar recordings on our website, usually 1 to 2 days after the webinar. And we'll send you an email with that link as well. So if you missed something or want to share this with your colleagues, you'll be able to do that later this week. So I know we have some new users and new people in the audience today. So I just wanted to give a quick introduction to DNA Star for anyone who's not familiar. Our brand that you may be familiar with is Lasergene, and Lasergene is comprehensive software for molecular biology, genomics, and structural biology, so both sequence and structure analysis. And we try to make our software as easy to use as possible. And also, we always keep accuracy at the forefront. So we create accurate, trusted results for whatever type of analysis that you're doing. In addition, we provide great customer support. So as I mentioned, Eric, who's here today, is part of that support team. We're happy to do one-on-one webinars. So if you see something here today and you maybe want to bring other people in or have a webinar with us to discuss your data, we're happy to do that with you. So as I mentioned, one component of our software is our molecular biology analysis tools. SeqMan Ultra is part of Lasergene Molecular Biology, specifically for Sanger or ABI sequence analysis. But Lasergene Molecular Biology is much more than that. Of course, we have cloning and primer design software, sequence editing, plasmid map creation, and things like multiple sequence alignment. We've done quite a few webinars on our molecular biology tools over the past couple months, and I'll show you some links to those webinars after Eric's presentation so you can see where to find those if you're interested in learning more about some of those applications. In addition, our Lasergene genomic software supports NGS analysis. We've got a long read assembler in beta that will be available with the Lasergene 17.1 release that's coming out. And this supports both de novo and reference guided workflows. SeqMan Ultra is also part of Lasergene Genomics. Today, we're going to be focusing on Sanger assembly and analysis. But if you have questions about NGS analysis, we can certainly help you with those. The genomic software does support all next-gen sequencing platforms. As I mentioned, we're also adding support for long-read technologies and a wide variety of workflows. So we have other webinars on this, and we'll have more in the future. But just to let you know, the SeqMan Ultra software that Eric's going to show today can be used in much the same way for these NGS technologies. In addition, for sequencing data, we have an annotation database and genome template packages to really help with variant analysis and other downstream analysis for your projects. And then finally, Lasergene includes structural biology. Lasergene Protein has tools for protein sequence analysis, protein structure prediction, as well as bioinformatics and structural analysis, things like epitope prediction and protein modeling, protein design. And all of these tools work together. So if you're doing, say, phage display screening with antibody sequences, you can actually analyze those sequences in the Lasergene molecular biology package. Eric's got a similar workflow that he's going to show today. And then if you had structure data, you could look at that as well. So today's demo is going to focus on SeqMan Ultra, as I said. This is a new application. It was introduced in February of this year. And as a new application, it's something we're working very hard on. We're continuing to add new features and improvements to it. So Lasergene 17.1 is coming out in just a few weeks, we believe. It will be this summer in the Northern Hemisphere. And it's going to include some new improvements, including multiple sample support, which you see in this image here. So we decided to use the Lasergene 17.1 software for today's demo, so you can see all the latest and greatest. If you're currently using SeqMan Ultra, you may see some differences between what Eric presents today and the software you have, but rest assured the new version of SeqMan Ultra will be available very soon. So for today's demo, Eric's going to show a de novo assembly project with ABI Sanger data, and including some downstream analysis options for translation, alignment, and tree creation. Then he's going to show you a templated workflow, including this new multiple sample support, as well as variant analysis. And as I mentioned, Lasergene 17.1 will come soon. So this is going to have some improvements to SeqMan Ultra and SeqMan Engine. So that's for Sanger and NGS assemblies. It's also going to have some new features for editing multiple sequence alignments, generating phylogenetic trees and editing them, as well as a new batch cloning workflow in SeqBuilder Pro. So if you're interested in any of these features, let me know and I can send you some more detailed information. So that's kind of where we're going today. I'm going to go ahead and turn it over to Eric for the software demo.
Thank you, Katie. So for today's demo, I'm going to show you two different workflows. So the first one will be a de novo Sanger ABI sequence alignment. And in this example, I'm trying to determine the diversity of antibody heavy chains, specifically the variable regions. And I have sequenced a small set of heavy chain mRNAs using a common primer site. And I want to compare them at the protein sequence level. So this will be a three-step process. The first step, I'll use SeqMan Ultra to align the set of sequences. And I'll do a batch editing so that they all start a common ATG start site. And then for the second step, I'm going to do a batch translation of all the sequences from DNA to protein sequence. And then for the final step, I'm going to do a multiple sequence alignment of the translated sequences and then make a phylogenetic tree out of it. And for the second workflow, I'm going to show you a reference-guided Sanger ABI sequence alignment. And in this example, I'm just going to align samples to a reference CDS sequence and then perform variant analysis. So when you're aligning Sanger ABI sequences, the program that you want to use would be SeqMan Ultra. This is our new Sanger ABI sequence assembler. And to start a new project, you just choose new assembly. And then under the molecular biology section, choose de novo assembly. And this will open up a wizard to kind of guide you through on setting up the project. So on the first page, that's the input sequences page. So this is the page where you would add the ABI sequences. And you can always just drag and drop the sequences into the window. Or you can always use a add button to manually look for the files from a specific location on your computer. And down here on the bottom right corner, you can see there's a run button. So if you just sequence a gene or a construct of some type, and you just want to do an alignment and using the default parameters, you always have the option to choose a run now, and that will assemble the sequences using the default parameters. But for this specific project, I would actually need to change the parameters. So I'm actually going to go through the whole setup process to kind of show you on how to set all that up. So once I've added my sequences, I just click next. And in the pre-assembly options page, you have the option to set the quality end trimming, as well as to do a factor adapter scan or contaminant scan or repeat scan. And if you would need to do a quality end trimming, you can go into advanced options, and that will show you, that will open up a window with the trimming parameters. For quality end trimming, there's a low, medium, high, or custom stringency. For what I'm doing, I'm just gonna stick with medium. We also have a function that will allow you to do a fixed end trimming. So let's say you want to trim off a specific number of bases in the beginning or at the end of the sequences. So for example, let's say I want to trim off the first 50 bases for all my sequences at the 5' end. I can do it under the fixed end trimming option, check the box for 5' end, and then enter the number of bases that you want to trim off. But for this, just to stick with using the default, since all the parameters is already optimized. And in here, you also have the option to see the parameters for the contaminant and factor scan. Again, the parameters here is already optimized, so there's not really a reason you would ever need to change it. But if you do need to make a change, you can do it in this advanced options window. And then for the next step, this will take you to the assembly options page. Since I'm doing a de novo assembly, I need to provide an estimate of the contact length. And for this specific project, it will just be about 900 base pair. And in here, you also have the options to change the merge size and minimum match percentage. Again, all this is optimized, but actually for this specific project, since I'm dealing with the variable region of the antibody sequences, I will actually need to lower the minimum match percentage from 70% to 50%, just to make sure all my sequences will align together. So here, change the minimum match percentage from 70 to 50. And then from here, just click next. And this will take you to the output page. And in the project name, you just enter the project name. And then specify an output location and where to save the project. And in the output section, you'll see there's an SQD project being saved, and that's a Sanger project that you can visualize and do some type of editing. There's also a context sequence, and that would be the consensus sequence for all the context in the project. And you also see a .script file, and that will have all the parameters of the assembly in it. Then you choose next, and this will take you to the assembly project page. And this will give you some basic information on the input data, like the number of input read bases, the estimated coverage. And this will also give you an estimated requirement. For Sanger assembly, it'll work perfectly just fine pretty much on any PC or Mac. There's not really much requirement to it. But if you do working with NGS data, then they will definitely have a more stringent requirement, and you can find that information on our website regarding the hardware requirement to do NGS assembly. So when you're ready, just choose one assembly. And the assembly will go for the process, assemble the sequence. For a small data set like this, it just takes a couple of seconds to do it. Once it's done, just choose next. And this will give you a project report, and this will have some statistical information to kind of tell you about the assembly. So you can see there's the number of contacts, the number of assembled sequences, the contact length, as well as the parameters that you use to make the assembly. So when you're ready, just open assembly, and this will open up the project in SeqMan Ultra. So once you have the project open up in SeqMan Ultra, you'll get this main screen. And it will have some basic project detail like the contact N50. This doesn't really apply to what I'm doing, but if you're doing a de novo Sanger genome assembly, this will be a useful information to know. And this will also show you the number of contacts in the project, as well as the number of reads that were assembled. And up here in the project report, you can switch your project details, and this will bring up that statistical report to kind of tell you the information about the contact information, the assembled sequence information, as well as the assembly parameter. And that information is saved with the SeqMan Pro project, SeqMan Ultra project. So you always have a way to get to visualize this information if needed. And then on the right panel under the Explorer tab, this will show you a list of contigs. In this case, I only have a single contig, and the length is about 918 base pair, and it has 14 sequences in it. So from here, really the next step of what we want to do is just go straight to the alignment view. And to get to the alignment view, you can go to View from the menu bar, and then go to Alignment. Or you can just double click on the contig to open the alignment view for that contig. And you also have the option to open the alignment view by clicking on this little button right here on the top right side. So I'm just going to double click on contig 1. And this will open up the alignment view. And in this view, you'll see the consensus sequence. And if you click on the plus sign next to the consensus sequence, you'll see the reading frame. And then below that, you will see the coverage plot. And then down here in the left pane, you can see the sequence name. And here you can see the sequence name is kind of all randomized. So really the next thing that I want to do from here is to sort the sequences by name. And you can do that by clicking on this little blue icon up here, and then just sort the sequences by name. And up here, you can see there's a list of icons up here. So if you click on this magnifying search icon, you can do a search. So let's say I'm interested in finding a specific sequence in the consensus. Let's just do something simple, say ATT, GTT. You hit enter, and it will find the location. And if you click on the green arrow, it'll take you to the next location if that sequence is present in other location on the consensus. And if you want to see the quality score for each of the bases in the sequence, there's this little Q icon up here. Just click on that. And then you can click on show scores, and you can see the quality scores for each of the bases. For what I'm doing, I'm just gonna hide this. So this is more or less the alignment view. And if you want to change a presentation in terms of how things look in the alignment view, you can go into the Style tab on the right panel here. And you click on it, you have the option to change the font size. So let's say if you're on a big high resolution monitor and the font is a little hard to see, you can increase the font size if you want to. You can also change the font style. If you want to use a different font style, you can just change it in here. And if you want to change the font size for just a sample name, you can check this box and change the font size that way, and that will change the font size for the sample names. And under the alignment section, it will have the ability to allow you to whether to give the user the ability to edit the project or to prevent the user from making any editing at all. For what I'm doing, the default is fine. And if you want to make changes to the coloring, you can also do it in here. So here, you can see all the mismatches are highlighted in yellow. And if you want the coloring to be a different color, you can just, in the differences section, click on this little yellow icon. And let's say I want to change the coloring from yellow to light blue, and just choose a color that I want, and just click OK. And this will change the mismatches color to light blue in this case. So if you want to change any presentation style and coloring, you can always go under the Style tab and make your changes there. So now for the next step, really is I want to check the quality of the chromatogram or the trace data for each of the sequence. And to look at the trace data, I can just click on the little plus sign next to the sample name. And this will show you the chromatograms. And if you drag on the middle of the sequence, there's a little box that you can kind of zoom in and out to make things easier to see. And for zooming in and out, you also have the option to use this green horizontal bar to zoom in and out as well. So to check the quality of the chromatogram, really all I wanted to do is just scroll through the sequence to check for the quality. So for sample 2, you can see there's nice strong peaks. You don't see a lot of noise. Every peak is pretty distinct. So this is really good. And pretty much you just scroll through it and just take a look and see if there's anything happening. And you can see there's a lot of mismatches in the middle of this alignment. That's expected because I'm dealing with the variable region of the antibody. So that's what I would expect. So for sample 2, I'm just going to keep scrolling. You can see the peaks are very strong, sharp, very clean. You don't really see much noise there. So just really keep scrolling through it. And just keep scrolling through and take a look. You can see the signal just kind of started to fade away towards the end, but that's what you would expect with Sanger sequence data. But even with the lower signal, it's still pretty clean and the peaks are pretty distinct and sharp still, so that's good. So yeah, take a quick scroll through. Sample 2 looks fine for the chromatograms. So I'm just going to minimize this. And if you want to check the chromatograms for multiple sequences at once, what you need to do is just next on the plus sign next to the sequence name, just right click and choose expand all. And this will show the chromatogram for all the sequences at once. So let's say I want to look at the chromatogram for multiple sequences. Let's say 2, 7, and 8 at the same time. I can quickly do that by showing the chromatogram for all sequences. So I'm just going to do the same thing. I'll just look at sample 7 and sample 8 and look at the trace data for both samples at once. So you can see the signal, very sharp, very strong, very clean. It's not really much noise. That's great. And really just scroll through, take a look. Everything's still looking good. You can see there's very distinct peaks, still very clean. There's no issue there. Then again, you see the signal kind of just faded away a bit, but that's expected with Sanger. So yeah, I'm not really seeing an issue. So it looks fine. I'm not going to go through and look through the trace data for all sequences, but that's probably what you would want to do in real life and just look at the trace data for each of the sequence. And then the next thing that I want to do is I want to check the overall alignment quality. And this is just something I'm just going to spot check because I'm dealing with the variable region. So there's going to be a lot of mismatches in the middle of the alignment. So in the beginning here, you see the alignment is really tight. This is really what I would expect. But once you start looking for the alignment, once you got into the middle, you see there's a lot of mismatches, a lot of gapping. Again, this is dealing with the variable region. This is what I would expect. So you just keep scrolling through and say after position 490, you get a really tight and clean alignment again. So this is probably the heavy chain section of the antibody. So you just really keep scrolling through, very clean alignment. There's not really any mismatches at all. So that's great. So once I have spot checked the alignment and I have checked the trace data, and for this specific project, I have a heavy chain CDS. This is more or less my control for this project. And really what I want to check for to make sure all the antibody sequences that I have cover the entire reference CDS sequence. And to do that, I'm going to use the strategy view, which is really just the overview of the alignment. To get to the strategy view, click on View, go to Strategy, or you can click on this little button, the blue and dark blue arrow button up here on the upper right side, and click on that, and this will show you the strategy view. So this is really the overview of the alignment. And really what I want is I want to make sure all the sequences that I have cover the entire CDS reference. And in here, you can see sample number 11 and sample number 21 only cover, say, about 85, maybe 90% of my reference CDS. So what I want to do next is to figure out what is going on with sample 11 and number 21. So I'm going to go back to alignment view, go to sample number 11, and check the chromatogram and to see if there's something going on there. So expand, show the chromatogram. So you can see there's really nice strong peaks in the beginning of the sequence. It's not really a lot of noise, maybe in the beginning, but that's typical with Sanger. So you just scroll through and take a look. And you can see signal is really strong, very sharp peaks. Yeah, everything looks good so far. And then just keep scrolling. And once you get to position 505, you can see the sequence got trimmed by our quality trimmer. And if you want to see the section of the sequence that got trimmed back by the trimmer, you see this little gray icon, gray triangle icon next to the sequence name. You can just drag on that to show you the section that got trimmed back. And here you can see the reason why this section got trimmed back. That's because there's not really any signal at all. And to figure out why this sequence is truncated, you can look up that information. So if you see a truncated sequence, says some of the reasons of what could cause that would be potentially a secondary structure. You may have used too much DNA template, or you may be dealing with a repetitive region. In real life, you will need to kind of figure out what happened with sample number 11 and then just resequence the sample and use it in the analysis. But for this demo, I'm just going to delete it from my downstream analysis. And what you wanted to do for deleting the sequence, just select it and then just hit the delete key on the keyboard. It'll ask you if you want to remove the sequence and you just click OK. And this will remove sample number 11 from the alignment. And then the next step is you want to do the same thing for sample number 21, where it only covers about, say, 85% of the reference CDS. So let's take a look at sample number 21 and see what's going on there. So I'll just do the same thing, click on the plus sign to show the trace data. And you just take a look at the trace data. It's not quite a bit of noise in the beginning. Again, that's expected. And then you just really look through the chromatogram. You got really nice strong peaks, very clean, not really seeing an issue. Very strong signal. And you just scroll through and then you can kind of see the signal started to fade away around position 300 afterward. So you can see the signal fading away and it just ends at position, say what, 488. So let's see what happened there. So I'm going to drag on this little triangle at the end of the sequence, expand on it, and you can see the signal just pretty much fell off a cliff and there's no signal after that. So that's why our quality trimmer removed the section of the sequence. So this looks to be the same issue as sample number 11. And this issue is likely, again, due to potentially secondary structure, too much template, or you're dealing with a repetitive region. Again, in real life, you need to figure out what happened to sample 21 and then just resequence the data and then use it for your analysis. But for what I am doing, I'm just going to remove this from the alignment. So I'm just going to select it, choose delete to remove the sequence. So now that I have checked the alignment, I've checked the trace data for all the sequences, and I have removed all the truncated reads, I'm ready to move on to the next step, which is I want to trim all my sequences to the ATG start codon of my reference CDS. So to do that, really, I'm just going to select the section that I don't want and just remove it from the alignment. And you can just simply just drag and drop the section that you want to delete. Hit the delete key on your keyboard. And that will trim back the section. And If you need to do some manual trimming, you can always just manually use drag on the little triangle next to the sequence to do some manual trimming. So now I have all the sequences at the beginning of the ATG site. Now I want to do the same on the 3' end to make sure all my sequences are trimmed to just the termination codon. And in this case, that would be the TAG site on my reference. So what I want is to trim off this whole section after the TAG codon on the 3' end of the sequences. So, and to do that, just select and then scroll all the way to the end of the alignment, shift, click, and that will select the whole region. And then I just do the same thing, delete, and this will remove the whole section. And now I have my sequence trimmed to the ATG site on the 5' end, and I have all the sequences now trimmed to the TAG termination codon on the 3' end. Now I'm ready to move on to the next step, which is to export all the sequences. So I can use it for downstream analysis and for doing the batch translation. So to export the sequences, you go to config, and then choose export sequences. And this will give you the option to save the sequences in a multi-sequence FASTA file, or you can save each sequence as its own file if you choose a multiple files option. And it will also give you the option to save it in different format. You can save it in FASTA or GenBank format. But for what I'm doing, single file FASTA format is fine, and I'm just gonna click OK. And it will ask you to pick a location to save that file. And I already have the file saved, but I'll just save it again. Replace it. And now we are ready to move on to part 2, which is to batch translate all the sequences from DNA to protein sequences. So, and to do that, I'm going to use a program called SeqNinja. This is a multi-purpose sequence editing program. And some of the most commonly used functions for SeqNinja would be to batch reverse complement sequences, batch translation from DNA to protein sequences, as well as to convert file type. So for example, if you have a bunch of GenBank files and you need the sequences in FASTA format, you can use this function to batch convert all your GenBank files into FASTA format. So for what I wanted to do, I just need to do the translation. So pick this function. And I just pick the file that I just saved from SeqMan Ultra. Just choose open and this will give you the translation option. For what I'm doing, I can just use the default. So I can just use a standard genetic code, standard reading frame. But if you do need to change the reading frame and genetic code, you can always just click on the drop down and pick the one that you want to use. Then I want to save my results in a single file. And for saving the project format, you can pick FASTA, GenBank, or Lasergene protein file format. For what I need, FASTA is fine. And then you just choose run. I already have a file saved already, so yeah, you can replace it. And then just click OK. And this pretty much covered the step 2 for translating the sequences. And that's one thing that I would kind of want to do is to open it up in a text editor just to make sure everything looks good. So let me go back to the project. And I think I save it here. So for the translated sequences, I will just open it up in the text editor. You can use Universal Viewer or Notepad++. Either one will work just fine. And I just want to kind of spot check to make sure everything is there. So what I wanted to check for is just make sure all the sequences are there. All the sequences is translated properly. You know, it all starts with an M, the methionine. It also ends with a termination. which is in this case a period. Quick look, looks good. So everything looks fine. So now we are ready to move on to the final step. And the final step is to do a multiple sequence alignment and really just to make a phylogenetic tree out of it. And for the phylogenetic tree, for making the phylogenetic tree and doing the multiple sequence alignment, I'll use a program called MakeAlign Pro. MakeAlign Pro is a multiple sequence aligner software. It supports some of the most common alignment algorithms, such as cluster omega, cluster W, as well as muscle. To start my multiple sequence alignment project, I open up MakeAlign Pro, choose a new project, and I just start a new alignment project. So from here, I'm just going to drag and drop my file that I just saved from SeqNinja into the window. And this will ask you whether the sequence DNA, RNA, or protein. In this case, it's a protein sequence, so I'm going to choose protein. And this will add all the sequences into the project. And really, the next step, all you need to do is just do the alignment. So to do the alignment, click on Align in the top menu bar, and you just pick one of the alignment options. For what I am doing, any one of them will work. So, and I know cluster omega and muscle is probably the two most used alignment algorithm out there. So I'm just gonna pick one of them. So I'm just gonna use muscle. And the alignment for something this small is pretty quick. And after you have done the alignment, what I want to do is just check the alignment to make sure there's no major misalignment that happened. So you can see in the beginning, you got a very tight alignment. And then once you scroll through towards the middle end of the sequence, you can see there's a lot of mismatches. This is really what I would expect to see. Again, I'm dealing with the variable region of the antibody sequence. So that's really what I expect. And then towards the end, you got a really tight alignment, looks clean. So yeah, I would say the alignment overall looks pretty good. And then really my end goal for this project is just to make a phylogenetic tree. So from here on the bottom, you can see there's a distance tab. And I can click on it and that will show you the distance table. And for what I really want, I just want to see the tree. And I can just click on this tree button at the bottom to visualize a phylogenetic tree. And on the right panel, under the Style tab, under the tree section, you can kind of play around with the layout. If you want to change the layout of the tree, you can just pick one of the layout option, and this will automatically update the layout for the tree. For what I do, and if you also want to change the font size and the coloring, you can also do it here. But really, I just need to get a tree out of this. Once I get my tree, I can either print this as a PDF or I can export this as a data, and you can use that information for additional downstream analysis if you want. So that's pretty much it for the de novo assembly live demo. So just let me close this and we will switch to the reference guided assembly for variant analysis. So for my second workflow that I'm going to show you, it'll be a reference guided Sanger ABI sequence alignment. And it will be a pretty straightforward example. I'm just going to align some samples to a reference CDS sequence and then do a variant analysis. So for this project, I'm going to use SeqMan Ultra as my launch point. So just let me close this project. So SeqMan Ultra, back in the welcome screen, under the molecular biology section, you just choose a reference guided workflow. In terms of the overall project setup, it's pretty much the same as de novo assembly. So here, it'll ask you for the reference sequence, and I already have one that I downloaded from Ncbi, so I'm just going to use that. So the reference sequence that I'm using is a CDS of the SOS1B gene of Chromatogram. So I'm just going to drag and drop the file into the window. And again, you also always have the option to use the add button to add your sequence. If you want to do your alignment against the entire genome, you can also use our genome package that is curated by us, and it will have some of the most common, the genome package for some of the most common model organisms like human, chicken, E. coli. And if you're using something that's more non-model, you can always download this, the genome from Ncbi genome database. And to do that, just click on the download Ncbi genomes button up here. And that will open up the Ncbi genome downloader. So it's fetching the information from Ncbi. So if you're working with some, say bacteria or virus genome, just pick one, and then we just browse through the different organisms, and then you can just download the reference genome straight using this downloader. I already have my CDS reference, so I don't need to download anything. And in this screen, there's also an option for you to add a Vcf file. So let's say you have a list of known variants and it's already in Vcf format. You can add that information into the project by using this function. And we also have an option to let you add the BED file. The BED file is really used for targeted analysis. Most people really use it for NGS type of NGS variance analysis like exomes, targeted sequencing, maybe even cancer panel. I don't know if a lot of people will use that for Sanger, but if you have one, you're certainly more welcome to use it. So now that I have my reference sequence added, just choose Next. Let me just resize this a bit. Choose Next, and this will take you to the input sequences page where you add your sequence data. So I'm going to add my data. And then I'm going to set this up as a multi-sample project. So something new that we added in version 17.1 that's coming out in 2 weeks or so is this group selection tool. And this utility, this allows you to pick a unique portion of the sample sequence name to define the group name. So let's say I want to name my samples C2, C6, and C8. Instead of manually just typing, C2, C6, and C8, you can just pick a portion, the unique portion of the sequence name, select the section that you want as a group name, and the software will automatically group the sample name that way. So this way, you don't really have to manually enter, the experiment name. For something this small, it probably doesn't matter, but if you're working with a lot of samples, this would be a very useful utility to use for grouping your samples. And then another new thing that we added in version 17.1 is the ability to let you run the multiple samples in a single project. So basically what it does is it puts C2, C6, and C8, the alignments, into a single project. This is extremely powerful if you want to do any type of cross comparison. So if I want to, look for variant comparison between, say, C2, C6, and C8, I would definitely want to use this function to make sure all my samples is in a single assembly for easier visualization and cross comparison that way. So once I've grouped my samples, you just go Next. It'll ask you for control. In this case, I don't have one, so I'm just going to move on to the next page. This will take you back to the assembly options page, where you can change some of the assembly parameters. For this, it'll be the same parameters that you use for de novo assembly. And for this, I don't need to change anything. Everything's already optimized. So I'm just going to stick with the default, and I'm just going to choose Next. And this will take you to the analysis options page. and where you can kind of pick the variant detection method. For this, since I'm working with the CDS of the gene in Chromatogram, the diploid variant detection would be more applicable to what I'm doing. But if you're dealing with a virus or bacterial genome, you want to use a haploid variant detection. You can set a gender, but for what I'm doing, it doesn't really apply. But if you're working with, say, human genome data, it may be something useful that you can set. And then for filtering stringency, I'm just stick with the default. Detecting CNVs, copy number variations, it doesn't really apply to what I'm doing. That's really more for NGS type analysis. And I'm not really interested in big structure variation. All I'm looking for is just SNPs and maybe small indels. So I can just leave this check or uncheck it. Either way, it will work for me. And then from here, just choose next. And this will ask you for the output page. So you can enter in your project name, say Chromatogram analysis. And then you can pick a project folder, pick a location of where you want to save it. And this will and then down here will show you the assembly output. In version 17.1, we added a new function that lets you save the project as an editable output project file in SQD format. For what I'm doing, I'm just interested in looking at variants. I don't think I would need to do any editing at all, so I'm just gonna stick with the default to get the project in .assembly format. And once you're ready, click Next. And this will take you to the assembly project page. Again, it will show you some basic input information, like how many bases. And then down here, there's the estimated requirement. And once you're ready, just choose one assembly. The process itself is pretty quick. It takes about 10 to 15 seconds with something this small. And something new that we added is now we have the capability to automatically export the variants in Vcf format. And I know there are quite a few users that has asked for this function, and this is why we added it. So once the assembly is finished, just choose Next. And this will open up the project report. Again, it has some statistical information. But really from here, you just open the assemblies, and this will open it up in SeqMan Ultra. And back in the main screen, you get some basic information like number of variants that are in the project, number of references. And for variant analysis, what I really want to do is just really go straight into the variance table. And to do that, you can just click on the variance item in the menu bar and to show me the variant table. And this will show the table for this project. So you can see, a lot of the common information you will see in the Snip indel table. You see the sample name, and you can see the sample name is kind of all randomized and jumbled up. So I'm just going to sort this by sample name just to group all the SNPs from the same sample together. Here you can see the reference ID, and you can see the contact position, the reference position, what type of SNP variant it is, if it's just a SNP, or if it's an indel, like an insertion, or if there may be a deletion, it will also show you that information as well. And it will show you the reference base, and it will also show you the call base, which is the variant base in this case. I'll show the genotype. And in the impact column, if you have a mutation that's in the coding region of the sequence, it will show you whether the mutation causes a non-synonymous or synonymous mutation, or maybe in some cases, even a frame shift. And then you get the SNP percentage, the feature type, the feature name, pretty standard information that you would get in a SNP report. And you get the DNA change in the DNA change column, as well as the amino acid change. Again, you only see the amino acid change information if there's a variant like a SNP or indel in the coding region of the reference sequence. And then here you see the depth as well. And if you want to know more about what each of this information, like the definition and so forth, you can always go to help, SeqMan Ultra help, to look up that information to get the definition for it. So really, in a Snip report, what I want to do next is just really to look for variants. In this case, I'm not going to look through everything, so I'm just going to pick out something that may be interesting to look for. So let's look at a couple mutations and see if there's something interesting that we can find. So up here for sample C8 at position 56771, you can see there's a 14 base insertion. And that seems interesting. So I would want to take a look to see if this is something that's real. So what I want to do is just double click on it, and this will open up the alignment view. And in the alignment view, just let me collapse everything here. You will see the reference bases that are highlighted in orange. What those reference bases are, each of the sequence is the actual consensus for the sample. So this will be the consensus sequence for C2, this will be the consensus sequence for C6, and this will be the consensus sequence for C8. This is a very powerful and useful function if you're doing any type of cross comparison. So in this example, I'm seeing this 14 base mutation, and this is only happening in sample C8, and this is not happening in C6 or C2. So with this view, it kind of gives me information to quickly visualize to see if this mutation is happening in only one sample, two of the samples, or in all the samples. So to look at this mutation to see if this is real or not, I'm just going to click on this little plus sign next to what I would call the pseudo consensus. And then really just click on the plus sign to show the chromatogram to see if the sequence trace data validate that this is an actual mutation. So here, you can kind of zoom in and out again to make things easier to see. But here you can see this mutation is only picked up on the reverse read, but not on the forward read. But the problem is with the forward read, the sequence signal is pretty low. It's not what I would exactly call high quality versus what you would see in the reverse sequence, where you can see this really strong, clean signal. Data looks clean. So even though this is only showing up in the reverse read, I would say I'm confident enough to confirm that this is a SNP, an actual insertion. If you want to know actually where this insertion in relationship to the reference sequence, you can see this is a reference sequence up here. Click on the plus sign, and it will show you the feature. And in this case, you can see this insertion is actually in the Intron region between the exons of the SOS1B gene. So like I said before, even though this is only picked up on the reverse read, we got really strong clean signal, and I am confident enough to confirm that this is a SNP. So I'm going to go back, and I will just confirm this is a SNP in the SNP report. And to do that, you just right-click on the variant that you want to confirm or reject, and just choose that option. And once you confirm the variant, the basis will turn green to indicate that the variance is confirmed by you. So now let's take a look at another variant. Now let's look at something maybe in sample C6 and see if there's anything interesting. So you can see there's a set of mutation in the coding region in sample C6. So let's take a look at this frame shift at position 56695. And the Snip report and the alignment view is interactive. So if you pick on a location in the Snip report, it will automatically take you to that spot in the alignment view. So here you can see this mutation, this insertion is only in sample C6, but not in C2 and C8. So let's take a look at C6 and see what's going on here. So I want to expand on the individual sequences to see the chromatogram and just take a look at what's going on here. So you can see this insertion is only picked up on the forward reads, but this is not picked up in the reverse read, as you can see here. Signal for the forward reads, I mean, it's okay, not great comparing to the reverse reads, but for this one, I'm kind of 50-50. I'm not exactly sure that this is an actual insertion. If this is something of interest to me, I'll probably just resequence this specific section and check to see if this is an actual frame shift in this case. But for this, I'm not going to confirm this variant for right now. So let's take a look at one more variant, and let's do something in sample C2. And I know in sample C2, there isn't a whole lot interesting going on, so I'm just going to randomly pick a variant and look at it. So let's just pick this T to G mutation at reference position 56889, or the T to C mutation in 56887. So you can see this variant is actually present in both sample C2 and C6. But for this one, I'm just going to look at sample C2 to confirm that this is an actual variant. So again, I'll do the same thing, expand to show the chromatograms. You can see the signal for the reverse read is quite poor, but I got really good signal, very nice, clean, sharp peaks in the forward reads. And you can see there's definitely, a clear mutation indicated by the trace data here. Even though the mutation in the trace data is pretty poor, I can still see a pretty, definitive peak for the call base of a C. That's a mutation from T to C, and I see that in both reads. So I'm going to confirm that this is an actual real variant. So to do that, I'll just do the same thing, back to the position, right click, and just choose to confirm selected variants. So really, with variant analysis, you will really just look through the Snip report, look through the variants of interest, and then really just check the alignment, check the trace data, and just to make sure everything looks good, and to make sure the trace data, back up the mutation that you're seeing in the Snip report. And then final function that I want to show you in the Snip report is the function to allow you to filter down the Snip set. So if you click on this little filter icon up here, this will open up a window that lets you filter the variance by certain criteria. So let's say in this case, I'm only interested in non-synonymous mutation in my samples. So I would, under functional impact, I'll just uncheck the box for non-coding and non-synonymous, and just leave non-synonymous selected. I don't really care about the Snip percentage and all that, so I'm just going to leave that as default, and then just choose apply. Click OK, and then the Snip report will only show the variance that is classified as non-synonymous SNPs, or maybe even a frame shift. So yep, the filtering function is really useful if you're dealing with looking at a lot of variants, and you want to filter down the information to make that looking at it more manageable in that case. So yeah, that's pretty much it for my presentation. So Katie, you can take over again.
Sure, thank you, Eric. I just want to show a couple resources before we sign off here. So on our homepage, you'll notice we have this message up about trial software. We always offer 14-day free trials to anyone. But if you're an existing customer, we're also happy to offer you an extended temporary license for use at home. So if you're still working at home due to the coronavirus pandemic, we want to make sure you're still able to do your work. So if that's of interest to you, please let us know. Otherwise, you can email this support@dnastar.com address. And then more specific to this webinar, I wanted to point out our training page. This is where you can find help for SeqMan Ultra. Also, if anyone here is a long-time SeqMan Pro user, we have a transitioning guide on the website. And this has a whole section explaining how to transition from, each app that we've retired in recent years to the newer counterpart. And so most recently, we've added a section for transitioning from SeqMan Pro to SeqMan Ultra. This is a really nice guide if you're, really familiar with different aspects of the SeqMan Pro interface. It shows you what the equivalents are in SeqMan Ultra. And then back to the website, if you want to see a recording of this webinar, we'll have that under training webinars in the next few days. And here you can also see some of our recent webinars. So I did see a few questions coming in the Q&A about like phylogenetic trees or sequence editing. I highly recommend you check out some of our recent webinars on SeqBuilder Pro and Megaline Pro. Those are the applications where we do most of the sequence editing and sequence alignments. And then finally, under product updates, you can find information about the Lasergene 17.1 release. So as soon as this is available, this page will be updated, but you can see some information today on just what the new features in that software will be. So including some of the sequence assembly features Eric showed today, but also new sequence alignment, phylogenetic tree features, and new batch cloning workflow. And then on that page, you'll also see we're having another webinar on July 15th, where we'll show all of the new features in 17.1, including some of SeqMan Ultra's new features. And so if you want to learn more about the new release, we hope you'll join us for that webinar. So that's all for today. Thank you everyone for hanging out. Sorry we went a little over time, but we hope to see you again at a future webinar.